Okay, so this is part 3 of the talk. In the last section, we looked at the various types of computable functions, some increasing restrictions on them, getting the polyregular, regular, rational, and sequential functions, and their corresponding restrictions on the automata that compute them, from pebble transducers to two-way, one-way FSTs, and deterministic one-way FSTs. Then we classified various types of natural language processes according to these distinctions and saw that there was a surprising range of distinctions as well as a surprising dichotomy between what is attested and what isn't attested. So now we're going to see how these affect learning. Why do we care about learning? I'm going to highlight a paper that I wrote 2 years ago in the journal Language, which is entitled No Free Lunch in Linguistics or Machine Learning. And this is absolutely right. If you have an inductive inference system of the type that is increasingly popular in machine learning, and in particular in natural language processing, it contains a bias. Those biases constrain what it can and can't learn. Okay? Every inductive learning system learns because it can learn a particular class of functions and can't learn another particular class of functions. Right? There's no inductive learning algorithm that can learn every class of functions. Okay? So just because you don't know what these biases are doesn't mean they don't exist, right? So don't confuse the ignorance of biases with the absence of biases, okay? So how do you study these biases? Well, this is the domain of grammatical inference, right? What is the nature of these biases when you learn grammars from data? How do our encyclopedia of categories help? Well, they provide necessary and sufficient conditions on computable functions, and they provide target function classes for generalization and learning. So about a year later, I had worked on this project, very simple experiment done with host abduction at Stony Brook when we were both there, and Max Nelson and Brandon Prickett from UMass Amherst. And here we were looking at probing the generalization capacity of recurrent neural networks with reduplication. So we were interested in these RNN Encoder-Decoders, right? So a recurrent neural network encoder basically is an RNN that maps some sequence to a vector, and then another recurrent decoder language model conditioned on V takes the vector and then outputs an output sequence, right? So how expressive are they? Okay, we can ask that question just as we can ask, what is the expressivity of, say, a two-way transducer? Now, we were really interested, because we were looking at reduplication, on the networks that are augmented with attention mechanisms. So in a standard encoder-decoder, the encoded representation is the only link between the encoder and the decoder. Global attention allows a decoder to selectively pull information from hidden states of the encoder, and the formal language theory analog here is that a two-way finite state transducer has full access to the input by moving back and forth. Okay? So if you can see this when you map these out on heat maps, right? So you can look at the relationship between English sentences and French sentences when you translate from one to the other, decode one from the other by looking at what the attention mechanism is paying attention to, the attention head. So we are interested in looking at reduplication because it really evenly splits this line between the rational functions and the regular functions, as we just saw, right? So our test data were input-output mappings that were generated with two-way finite state transducers from the RedType database. Okay, RedType is a database of computable or computational models of two-way transducers that are generated according to a bunch of different reduplication patterns found across the world's languages, which you can find on GitHub. We looked at 3 different types here: initial CV copying, initial 2-syllable copying, and total reduplication. So we were really interested in fixed size bounded reduplication, fixed size, variable size but bounded reduplication, and invariably sized reduplication, right? Because this will test the rational regular boundary. So what we did was we generated 10,000 input-output forms for each language and split them standardly. We varied the input length, right? So we varied from 3 to whatever. We had an alphabet of 10, 16, or 26 characters and no boundary symbol present. First experiment, we did an interaction between reduplication type, recurrence, and detention. So we looked at total and partial reduplication. We looked at sRNNs, this element networks versus gated recurrent units, GRUs with and without attention. We had a max string length of 9 with a 10-symbol alphabet. And our hypothesis was that attention should improve function generalization across reduplication types and recurrence relations. So what are our results? So here's how you read this graph. On the vertical axis here we have generalization accuracy, right? The left-hand side here is the performance of the element-style simple RNN. The right-hand side is the performance of the gated recurrent units. We subdivide these into performance on the two-syllable reduplication and the total reduplication just so you can see the result. And then the black bars represent the networks that had attention mechanisms, and the salmon or pinkish colored networks are those that didn't have attention mechanisms. What you can draw from this is that the SRNNs are totally failing, right? They are, without attention, they are doing a little bit better than two-syllable and total, but still totally failing. I mean, less than 25% accuracy. The gated recurrent units, on the other hand, also notice this asymmetry between the two-syllable and the total reduplication, but much better performance, about 70 to 75%, but still not great. None of them are reliably generalizing the functions. However, those that are augmented with attention mechanisms, both SRNNs and GRUs, reliably succeed almost 100% accuracy on the test set, okay, and the data set. All right, so second experiment, right? Because we're interested in the behavior of this, gated recurrent unit, we really wanted to understand the relationship between the, features of the language. So we changed the alphabet size and the range of permitted string lengths with the hypothesis that the network generalization, while learning, a general reduplication function, which doesn't care about the input, should be invariant to language composition, right? It would be weird if you could only reduplicate up to length 5, right? It would be weird if a transducer could only do that, right? So we'd like to see if the networks do that as well. So here's the results of the second experiment. On the horizontal line here, or horizontal axis, we see the variation in alphabet size and then the generalization accuracy here. Again, we see that the networks with attention are performing at ceiling. The poor RNN without attention is just failing all the time. And the gated recurrent unit without attention is pretty decent performance when your alphabet size is 10, as in the original experiment, but when you start increasing it, it performs worse and worse and worse and worse. Now let's look at the variations in string length. Again, attention network's always at ceiling, doesn't care about the string length. The RNN with attention now does a little bit better, right? So with string length of 5, it's performing pretty well, but I mean, as soon as you start to increase it, it quickly fails. It quickly just loses its performance. The GRU without attention is also starting to see a decrease in performance relative to string length, slightly less than the RNN, but the overall trend is the same. Okay, so what can we conclude from this? Then we can conclude that networks with global attention learn and generalize all types of reduplication and seem robust to string length and alphabet size. The SRNNs without attention show slightly better generalization of partial reduplication than total, but there's a confound maybe with the less attested ones, or maybe there's a bias preferring the regular pattern, we don't really know. Now the GRUs perform better than the SRNNs, but they're not robust to the length of the alphabet, which means that even though they're performing better, they're just doing a heuristic, okay? So the general message is that networks that cannot see material in the input multiple times cannot learn generalizable reduplication. It's true of the two-way FSTs, it's true of the neural nets. Now, let's peek inside the neural net a bit, right? We saw before that you can use this heat map of the attention head to sort of understand what the relationship between the input and the output is, right? So we thought, oh, this might be an interesting way to see if it's really approximating the generating function that it was trained on, namely this two-way transducer. So recall this origin information. Origin information, or origin semantics of a transduction, is the relation between an input symbol and an output symbol, okay? So in a two-way transducer, right, remember it reads the symbol, or it reads the input multiple times, right? So from pat to pupat, it first reads a PA, rewinds, and then reads PAT, right? So both output Ps depend on reading this input P here, just as both output As depend on reading this input A. For a one-way transducer, that's not the case, right? Remember, it sort of memorizes. It can only move one direction, so it reads the reduplicant and then has to sort of memorize by outputting the whole APA. So the whole reduplicant relies on this single input A here, right, or the edge of the reduplicant, okay? So now, if we connect the origin information, right, to the heat map of what the attention network is paying attention to, I mean, they're basically the same, right? And now look, which one does it look more like, right? The two-way transducer or the one-way, right? So here we see both input P's are sort of looking at the same input segment, this P. Both input A's are looking at the same input segment here, right? The T is just looking at itself, right? Now, this is kind of a short example, so let's look at a slightly longer one. Here's pasta pasta po out from the input pasta po, and here is the input spavtov going to spavtov spavtov. So we have CV CV reduplication and then total reduplication here, right? Here it's pretty dramatic. You see the first reduplicant, rewind, read the whole thing, rewind, look at the whole thing again, right? So they're really approximating the underlying behavior of the two-way transducers. So the attention networks, not only do they succeed, but they succeed because they're emulating the behavior of the two-way transducer, exactly what we wanted to see. So summarize here, right? Partial and total reduplication is typologically common, as we saw, right? It inhabits restricted function classes. And this allows testing the generalization capacity of neural nets and connecting them to one-way or two-way finite state transducers. Attention is both necessary and sufficient for robustly learning and generalizing reduplication functions using encoder-decoders. Non-attention networks are limited to a single input pass, approximating the one-way finite state transducer. And the attention networks, approximating a two-way finite state transducer, can read the input again during the encoding. So support for this hypothesis comes from the attention weights, and there's an input-output correspondence relations which mirror the origin semantics of the two-way finite state transducer.